make sure that you're doing the work. And actually, I had somebody in this class who will remain nameless that asked for more problems, and I posted those on September 13th. So you do have more practice problems.
Zuhair, it says it on the...
Yeah, it does.
Thanks, Andrew. You're welcome, guys.
So again, I'm trying to give you as many types of problems to practice, but I can't do it for you. All right, so.
Are we getting another sheet to do today?
No, it's review, since the test is the next time we meet. So you have those, the packet, you definitely want to look over the packet.
It's pretty much just to do what you need to do. That's
Perfect.
Well, I have to say,
Yeah, you're
today and tomorrow. Why are these exceptions?
What's that?
Why are these, number one, why are they exceptions?
Well, like with...
Oh, well, I haven't even started yet. All right. So with that, that's a good segue. Number one, in general, the atomic mass of the elements increases as the atomic number increases. Find the pairs of elements in the periodic table that are exceptions to this generalization. And again, to explain why that takes place, just deals with how many neutrons are present. We can't control how many neutrons are actually present in the nucleus. That's not something I'm going to get worked up about. However, remember that the first periodic table based on Mendeleev was based on increasing atomic mass. So these are three that I found, but I've heard that there's like 6 or 7 instances. So think about flipping those elements. That would definitely mess things up. So just looking at the periodic table more than anything else. Number 2, write the symbol for the elements in the following locations. Be sure you can do this. This is easy points, guys. Especially if you know your 52 elements, names, and symbols, then it should be really easy. Now, tomorrow I will not give you Roman numerals. This seemed to give a lot of people conniption. 3. Make sure, guys, make sure you know how many electrons can occupy each type of orbital. Okay. For instance, what's the maximum number of electrons per orbital? 2. Okay. How many orbitals per energy level can S have? 1 orbital, so therefore 2 electrons. For the P's, how many orbitals? 3 orbitals. And then D is 5, and F we really don't care about, but know that there's 7. However, knowing how many orbitals we have, because I'm going to tell you, on the one question on the quiz where it asked you to draw out the electron configuration, I probably had about 4 or 5 people, not necessarily in this class, that didn't know how many orbitals were in the P's and the D's. I think they went 4 and 4. It was really odd. So make sure you know where the locations of the orbitals are on your periodic table and how many orbitals are. And then electrons. So if the question asks, name a third period element that has a half-filled p orbital, well, that deals with all the p's. So if there's 3 orbitals, 1 electron in each. So 3. So phosphorus. And you'll see more questions like that on the test, I promise. Number 4, identify the group by number and family if it's accepted. In other words, if we have a name for it. So, and again, a lot of people were getting really hung up. Don't always go with the first energy level because, again, hydrogen and helium are apart. So go like 2s2, 3s2, 4s2, and so on and so forth. So the last part there deals with group 2a metals, okay, or the alkali earth metals. Again, pick an energy level other than 1. Of course, there are no p's in the first energy level. So if you want 2s2, 2p5, these represent the halogens. Okay, so remember, groups or families are columns, the vertical things. Periods are rows. The electrons filling the d orbitals, I had you guys just put 3b through 2b, so anything in the d orbitals would have been acceptable. And then the last one, S2P6, deal with the noble gases. And just for kicks and giggles, make sure you know how many valence electrons are in each of these. Okay.
So it'd be 2, 7.
2, 7.
3 or
2.
2, 5.
Because again, valence electrons only deal with outermost s and p. So these guys only have s orbital electrons. Now I won't ask you that on the test for d orbitals, but you might need to move some of those s orbital electrons to make a d orbital half full or full. just like we talked about this.
Could you set up a question like that for me, so I could review it later? So I don't-
Could we do what now?
Like what you just told me to know?
No, the special stability rules.
Oh, okay.
Yeah.
Just watch the video.
Yeah.
With the 3B and a 2B, can we put that as 1B to 18?
The weird thing about the periodic table is it starts with 2B. What's that?
It goes from like 3 to 8, 1 to 2.
Does it go from 3? I thought it went from 2 to 3. Oh, it does go from 3 to 2. You're right.
I have 3 to 2.
Yeah. I do have 3 to 2.
Yeah.
Okay. But go from where it begins.
Okay.
Yeah, I'm sorry. Make sure you know how many valence electrons there are. And again, valence electrons are located in which orbitals? S and P. S and P. No D's, no S. So the oxygen family, group 6A, so 6. Sodium is in group 1A, so 1. Elements in group 3A, I'm sorry, element in group 3A, period 5. We don't care about the 5, but we do care about the 3.
Can you explain that?
Explain this one.
How to do it?
Find the element, go all the way to the top. Whatever A it is, that's how many valence electrons. Again, it's the number of electrons in the outermost S and P orbitals.
So it'll never be.
So you.
So no B's. Whatever column it's in, go up, and you'll see a number and a letter A. That tells you how many valence electrons. And then, why is this one 7 and not 9?
Because the 2s squared isn't an outermost s orbital, is it?
The 1s2 you said?
No, the 1s2 is an outermost orbital, but the 2s2 isn't.
Actually, it's flipped. The 2s are the outermost. In other words, whichever row the element's in, that S and P orbitals are the valence. Predicted number of protons and electrons in stable ions of radium and iodine. Some of you were having concerns with stable ions. Most common charge. All right. So we're looking at, does something want to lose electrons or gain electrons? And again, metals want to do what? Lose, and metals want to gain. Non-metals want to gain. So when we look at metals, how many valence electrons do they want to have after they lose? 0. And then the non-metals want 8. So keeping that in mind is going to help you in answering these questions. Now radium, is that one of our 52? I honestly can't remember.
Yeah.
Okay. So radium is symbol Ra, and it will always have 88 protons. No matter how many electrons it has, it'll always have 88 because protons identify what we're looking at. So therefore, when it's neutral, it'll have 88 electrons. Now since radium's in group 2A, it wants to lose 2 electrons rather than gain 6 more. So if it loses 2 electrons, what charge will radium have?
+2.
Very good. So it loses, it becomes more positive. If it gains, like iodine, who has 53 protons, it's actually in group 7A, it needs 1 more electron to have an octet, or 8 electrons. Therefore, iodine will have what charge?
-1.
Good. I'm sorry?
It's on the period.
All right, number 7. What does the principal quantum number n designate?
N.
The energy level, or even the size. Okay, either of those is acceptable. What does the second principal quantum number represent? The first one represents the energy or the size, how big it is. What does the second principal quantum number represent? Shape. Very good. Whether you're looking at S orbital, P orbital, D orbital, or F orbital. You'll need to know that for tomorrow. What does the third principal quantum number represent? Orientation. Good. So whether it's on the x-axis, the y-axis, or a combination of any of those 3. Okay. And then the fourth one deals with spin. So whose principle states that no 2 electrons can have the same spin? The P one.
There's a person.
There's a person.
Planck.
Pauli, very good. So Pauli exclusion principle states that 2 electrons have to have opposing spins. Pauli. There's just a lot of stuff.
Yep.
And then there's another guy that states that you cannot predict the path of an electron as it moves around in its orbit. Does anybody remember what that is? It's something uncertainty principle. Tony's uncertainty principle. Starts with an H, I'll give you that. Heisenberg, very good. Okay. There's a reason why I'm telling you this, so good.
So that it'll be on the
Wait,
video.
so
Was that guy
the
Hun?
scientist
Is
people?
that Hun's rule?
No, that was Hund's rule states that we're going to drop electrons closest to the nucleus or in the lowest energy levels before we fill them in the higher. So Heisenberg is the one that's the uncertainty.
And
So you got Pauli in. Huh?
They can't spin the same way.
That's Pauli. Yeah, they don't spin in the same direction.
They can have
Good.
the first three quantum things work the same except the last one, that's what it says.
And that would be because of the spin. Good. For the video, Ariel said that you can have the first three principal quantum numbers, but the fourth one can't be the same.
Yeah,
What about orbital? Can they have the first three principal quantum numbers be the same for two orbitals?
No.
No, not for orbitals because the third one deals with orientation. So again, it'd be like having two p orbitals along the x-axis. Not gonna
You know
happen.
that for a test?
Wouldn't hurt.
Wait, what was that again?
I'm just gonna watch this video about 20 times.
Right?
So with an electron, it cannot have the same four principal quantum numbers. With an orbital, it can't have the same first three.
Okay.
Yeah.
I'll forget.
All right, number 8. Okay, number 8 is a lot like number 6. That was probably the most asked question last night. Predict the common ions formed when atoms of the elements listed gain or lose electrons. So again, you need to know what the tendencies are. Do metals want to lose electrons or gain electrons? If so, how many? Then name the noble gas in which the ion is isoelectronic. What's isoelectronic mean?
Oh, so
Same
you
electron
have same
configuration.
electron configuration.
Configuration.
I knew
Did
that.
Kate beat you all?
So the same electron configuration. Very good. And I will not ask you for anything other than being isoelectronic with another noble gas. Okay, so we're always going to go with the same electron configuration as the nearest noble gas. All right, so looking at magnesium, being a metal in group 2A, wants to lose 2 electrons, therefore it'll be +2 charge and isoelectronic with neon.
We need to have it in brackets.
Nah, that's okay.
You just put in brackets.
I was being cool.
Oh.
Chlorine wants to gain 1 electron, therefore it'll be isoelectronic with argon. Good, not arsenic, argon. Letter C, aluminum will lose 3 electrons and have the same have the same electron configuration as neon or be isoelectronic. Letter D, potassium, group 1A metal, wants to lose 1 electron, therefore to be isoelectronic with argon. Sulfur, group 6A, wants to gain 2 more electrons. Again, sulfur has 6. To get 8, it needs to gain 2 more. Okay. Barium, a group 2A metal, will lose 2 electrons. When it loses the 2 electrons, it'll have the same electron configuration as xenon. Now notice that when we're doing this, you're never going to have a charge greater than 3 or less than 3 at this point. Okay, so +3 or -3 at this point. Now that'll change later on in the year. I just want you to learn the basics.
Yeah, dude, we should have this stuff down. We're talking about big electron charges.
All right, number 9. I have a couple questions similar to this because you'll see it on the test. The first 3 ionization energies of an element, and don't worry about the mole unit here. We haven't talked about a mole, but at least kilojoules are. We have first ionization energy to remove the first electron is 403. Second ionization energy to remove the second electron is 2632, and the third ionization energy to remove the third electron is 3859. Question asking, what is the charge on the most common ion of this element with this data? And how many valence electrons does the element have? Identify the element as either gallium, rubidium, or barium. So the question is, when you look at this, how many electrons are easy to remove before we start taking from the core?
1.
1. Very good. So you want to look for between the first ionization energy and the second ionization energy. Is there a jump of over 4 times or 400%?
Yes.
If the answer is yes, then the first is easy, everybody else is hard. Okay? What that means is we can remove this valence electron rather easily. Now we're pulling electrons from the rows above, or the full orbitals, and atoms don't like that. So since one electron's easy to remove, that means that that element comes from which group?
1A.
1A. If two electrons are easy to remove, it comes from group
2A.
2A. And I won't go any higher than 3A. Shocking.
You better not.
So, since it's easy to remove one electron, that means we're going to take one electron away. This is the only element that is in group 1A, which is rubidium.
What's that extra stuff, the K on?
What's that? Oh, that's just the shorthand. Is that, yeah.
I think that RB.
And I didn't ask you to do that.
Okay.
What happened?
Wouldn't RB be the shorthand as opposed to writing out KR in brackets and 5S1?
Not sure what you're at, but okay.
Wouldn't it be easier to just write RB?
Yeah, but over and above. It's called being an overachiever. Today is nerd day, right?
The term
Come
is
on.
above and beyond.
Well, Shane is not dressed up like a nerd.
Seriously.
All right, number 10, use the position on the periodic table to determine the number of d-orbital electrons for iron, zinc, and chromium. Now remember, when we're looking at elements in 3D and 4D, we have to be aware that there might be special stability rules in play. So with iron, is it possible to take electrons from the s orbitals and move it to the d's to make a half-filled or full d
No.
orbital? No.
No, sir.
So we got to leave it as is. So there's actually 6 valence electrons, or I'm sorry, 6 electrons in the d orbitals. Zinc is full. Okay, the s and the d are full, so you don't want to try to move anybody. We never move electrons ahead to the p's. Don't do that. So zinc has 10. Chromium. What do we do with chromium?
You have to change it, and it would be half filled.
Good. So since special stabilities are in play here, the correct answer would be that chromium would have 5 d orbital electrons. Okay. We would take one from the s and place it in the d to make a half-filled s and half-filled d.
Did we need a shorthand there too?
No, I was just asking for how many. Again, over and above.
Just say that, Shane.
Very true.
I'm sorry. Number 11, what element has the electron configuration? Be sure you can do those. Okay, so again, just rewriting what we did up here. So titanium and chromium. Easy points, right?
Oh yeah. All day, great.
I know, right? Number 12, which transition metal ion, and again, an ion is what? What's an ion?
An atom with any charge.
With a charge, good. So it's a charged particle. So it has lost or gained some electrons from the original amount that it had. So which transition metal ion, scandium with a +3 or zinc with a +2, is isoelectronic with argon?
Scandium with a +3.
Why?
Because I said so.
Okay.
It's zinc +2. If you go back 2, it won't be argon.
Very good. It's all about the same number of electrons as well as the same configuration. So when you look at scandium, yeah, I've got 3 electrons. If I lose those, I'll be isoelectronic with argon. However, zinc, if I take 2 away, I'm just taking them from the s. I still have all those d electrons. So again, isoelectronic means same electron configuration. Also, same number of electrons. Okay. 13, for which of the following elements do you expect there to be a very large increase going from the second to the third ionization energy? So this is piggybacking off of question 9. Okay, so it's just another way to restate it. So how many electrons are easy to remove?
2.
2. Therefore, this choice is in which group?
2A.
2A. Which is in group 2A?
Magnesium.
Magnesium. Okay. Magnesium.
Sounds like Sean Connery.
14. What trend is observed for the atomic radius of atoms? Going down a group or going down a column?
Large.
They get larger.
Bigger.
They get bigger. Why?
I don't
Because
remember
there's more
why.
electrons.
What's that?
More electrons.
More electrons that we're placing in more energy levels. So as we move down, we're filling up energy levels or orbitals. So the more electrons you have, the bigger you're going to be, as long as you're adding them to. Going left to right along a period. So if we're looking at the periodic table and we go in this
Get
direction,
smaller.
get small. What's that?
Electrons.
No, it's gaining electrons, but it's filling up what?
More or less orbitals.
The S&P orbitals. So it's becoming more possessive. So
That's what he said.
as we acquire more electrons in that energy level, like nonmetals, do they want to lose or gain electrons? Nonmetals. They want to gain electrons because they're almost to the octet. So as they get more and more, they acquire more, they bring them in. They don't want to lose them. However, the metals are like, I just want to give them away. So it just relaxes, teases all the other elements out there. Okay. So as you get more and more electrons along the same row, not column, along the same row, those other electrons are drawn in closer. All right, number 15. How does core electron shielding affect the attraction of the nucleus for the valence electrons? Now, bad news. I most likely won't ask a question dealing with core electron shielding. Okay. But do realize that when we talk about core or electron shielding, that if this is the nucleus and I'm a bigger atom with many orbitals with electrons in them, and I'm an electron out here, okay, as an electron with a negative charge and the nucleus with a positive charge because it has the protons, I'm not feeling or sensing the positive charge as much because I have all this negative influence in between, so it acts as a shield. So that's another reason why the bigger you get as an atom, the easier it is to lose this electron, because all this negative influence isn't allowing this electron to experience the positive effect. Okay, so don't get excited over this question. All right.
That's exactly what
So my answer was the valence electrons are easier to move than core electrons.
Sounds good. I'll go with that. All right, 16. So if you want to circle 15 and say, I'm not going to lose any sleep over this, that's probably a good idea. All right, 16. What is the ionization energy and how's it determined? Ooh, what is ionization?
Energy needed to use
remove
electrons.
Use electrons, and it's experimental.
All right, so ionization energy is the amount of energy to remove an electron. Is that what you said?
That's what I meant. Yeah.
Okay, good. So it's the amount of energy to remove an electron. Now, what would you guess that the ionization energies for metals are higher or lower than nonmetals?
Lower.
Very good, lower. Okay, because again, metals want to lose electrons where nonmetals don't want to lose them. And then
So,
Stephanie said that
determined by-
it's determined. You got to go in the lab. I won't ask you about that. But do know what ionization energy is. That part.
Wait, show how.
You got to go do a lab. All right, number 17. Why does sodium have a higher second ionization energy than the first?
Because it's first in the column.
Go on.
Comes from the core,
Which one?
the second.
The second one, we're pulling electrons from the core. You're making Shane all mad. He wanted to answer that. So Shane, where's the first electron coming from?
The valence electron.
Very nice. So we can remove the first one because it's valence. The second one we're ripping from the core. Now again, that second one's not impossible. It's just going to take a lot of work and a lot of energy to get that
So
out.
what's the actual antonym? Like what should we write down?
The second electron is being removed from the core, where the first one is the valence electron. Valence, no problem. So we would have a big jump of at least 400% in energy to remove the second electron as opposed to the first one. 18. Which has a larger radius, sodium with +1 charge or neon neutral? Explain your answer. Now, let me ask you this. Do they both have the same number of electrons?
Yes.
Yeah. Do they have the same number of protons?
Yeah.
No.
Who has more protons?
The Na.
The sodium. Very good. Now again, remember the nucleus is really small compared to the orbitals.
So they're the same type.
They're not the same size. Here's what I want you to visualize, or to visualize, not visualize, but to visualize that the sodium has more of a positive charge, but the same number of electrons. Actually, the sodium has an additional positive charge, which brings those remaining electrons closer in.
Should be Ne.
So it'd be sodium with a +1.
Oh.
And also think, gravitationally speaking, and know you guys haven't had physics yet, but the more gravitational mass you have, the greater that attraction for those electrons
But if you
is.
said it brings it in, wouldn't that make it smaller?
Correct.
So
So
we can
sodium
think of it
+1 would
kinda
be
like the
smaller.
solar system.
So the neon's large. I will
Correct.
not ask you a question like this tomorrow on the test. However, I will ask you a question: which is bigger, sodium with a +1 or neutral sodium? Which one's
Which
bigger?
would still be neon.
Neutral.
Neutral.
Oh.
The more negative the atom is, the bigger it is. Okay.
So it's always neutral. Always neutral.
Well, or negative. The more negative the
Well,
element.
yeah.
And I think we have some like this, don't we?
I think, yeah.
Okay.
20 is like that.
What trend in the ionic radius of an element would you predict as you move down a family?
It gets larger.
It's larger.
Yeah, it gets bigger regardless if it's neutral or an ion. Now, I won't ask you left or right. I won't do that.
So that gets smaller, doesn't it?
No, it depends on the element.
What?
All right, 20. Which of the following would you predict to be larger? The more negative is the larger. Okay? So Na +1 is positive, where Na is more negative than +1.
And then F -1.
Very good. And I'll make sure I space that out.
And then
Fe negative
And then H -1.
What, Tony?
one.
Fe negative
F,
1?
My bad. F negative 1.
Oh, okay.
Tony, dude,
Fe.
you're behind us.
And D, hydrogen with a -1 charge.
I just beat him.
Tony, you're behind us, my friend.
23. What elements are composed of the atoms having the following electron configuration? And all are neutral.
Sulfur.
Good.
Manganese.
Neon.
The mainless of all elements.
Arsenic.
Arsenic. It'll kill you.
Neon.
I don't know.
Mo.
Molly.
Again, some more math problems. Make sure you can do this. Make sure you know what the symbols represent, the units associated with that. I'm finding a lot of people just conveniently leaving the units off, and that's not good.
I only did
Because generally when they leave the units off, they forget to do things, and the units will tell you what you're doing. Again, if you need to rearrange the variables, make sure you do so. Be sure that you show the variables before you do any math. All right? Even if it's this, and we're not rearranging, still show this before you plug any values.
Get to the next one.
All right.
Why don't you put on this 6.17 times 10 to the 14th? Why don't you put HZ on the end of that?
Okay. My recommendation is that you write 1/seconds so that the units can cancel out. I wouldn't write HZ because that doesn't tell you where the second is.
1/2.
But if it's 1/second, then you know, oh, okay, the seconds will cancel.
And if you put like J seconds in your answer, would that be wrong?
That would be incorrect because you probably had hertz there and you didn't have anything to cancel out.
Oh, so that's okay. So
Yeah.
that explains it. And is it okay if I had 4.10 times 10 to the negative 19?
As long as you showed all of this
Yeah, I
and
did.
this and the units and the correct, yeah.
Yeah. Okay.
All right, number 25. It's asking for the wavelength, and it gave you the energy, so you get to use two equations.
Awesome.
So take what you know, or what you are given, and change it to what? Since we're looking for wavelength, what do we have to know that's in both of those equations?
Frequency.
Frequency, or the V. Okay, that's frequency.
So we need to put E over H for that?
So we need to have E over H, and show this before you plug any values in. Show your units so that they cancel out. We're left with 1/seconds. And I wouldn't write hertz here because we're going to do something with this value. Now you use the speed of light equation. Again, that's wavelength. Lambda's wavelength. Rearrange that so we get our wavelength. So now we have speed of light over the frequency. I don't care how you're showing the units, but again, I will always have one divisor in my problem. And then make sure you know how many nanometers are in a meter. I still am stunned by that.
10 to the 9.
10 to the 9, not -9, 10 to the 9.
There's never negative.
There's never a negative within the problem, okay? Unless I've given it to you. That would be something you would start with, or if it's a constant. But on the metric to metric conversions, never use negatives, okay? Because if I move the decimal place to the left 9 times, or if I move it to the right 9 times, it's still 9 times. So Don't do that.
I think my earbuds on.
All right, and then 26. It wants to know what is the wavelength. So again, change that hertz into 1/seconds and solve. And again, on the calendar, where it says September 13th, or at least 2012, we do have more of those types of problems. What's that, Tony?
Can you go back up to 25 real quick?
Oh,
Yeah.
yeah, you can,
Final answer. Thank you.
Okay. Again, if you're still having issues with writing electron configurations, doing the math, September 13th. Also, make sure that you're looking at your packet. There's a lot of things that we didn't talk about, like the light. Make sure you know who has more energy, who has bigger wavelengths, frequency, things like that. I will ask questions about information in the packet as well. So the review guide does not cover everything. Okay.
How much, what percent of the test does it cover?
At least 70% of it.
Oh, God.
Yeah. I mean, I didn't want this review guide to be 5 or 6
How long
pages.
was our test?
50 minutes. You'll go at blazing speed. Because you guys are taking it on Friday, so you have the shortened period. That's why I reduced the test down. Yeah.
We have a reduced test.
A couple 3. Yeah. There'll be enough. There'll be enough.